So here's our regression equation. Let's see, how far do we want to go? So we'll go a little bit and then we'll take a break. So here's our logistic regression equation. And that regression coefficient, that V1, our slope, our regression coefficient for whatever x is just telling you the increase in the log odds of your outcome with a unit increase in x. So what's the change? If I increase parent education by 1 year, what's the change in the log odds of dropping out? Or I increase it another year, what's the change in the log odds of dropping out? But again, that doesn't really help us very much. I get confused thinking about what log odds are. So a beautiful thing, there's this beautiful thing or a beautiful relationship here with those regression coefficients and log odds. That if you take we can convert the regression coefficients into odds ratios. So instead of talking about a unit increase, the effect of a unit increase in log odds, we can talk about the increased odds rate. We can talk about this as an odds ratio. Let me kind of explain that for a second. Instead of, if we take the regression coefficient, raise e, that 2.71, that natural logarithm, you'll also see it on output or on your calculator. Instead of being the little e, it may be exp. That's just the same thing. If you see exp, it's the same as e. So, or exp in parentheses b is saying take e raised to the power of the regression coefficient. And that gives you a different type of odds ratio. It's a little different than the odds ratio we talked about a minute ago. But it's very, very similar. And what it's telling you, if I've got a unit, what's the increased odds? E to the b is telling me what's the increased odds of the outcome with a unit increase in x. I'm walking the wrong way, right? A unit increase. So if I increase 1 year's education, don't worry about, well, I'm not going to try to interpret the b as log odds. Instead, I'm going to take that regression coefficient, raise e to the power of b, and calculate my odds ratio. And what this tells me is if a 1 unit increase in x, my odds go up, e to the b. So the odds of the child dropping out go up or down. Because it could be going, we'll see in just a sec. So what's the change in the odds of the outcome with a unit increase in x? It's not the same as the odds ratio that we described earlier. And I'd actually, if it was up to me, we would pass a law and we would always refer to these as logistic regression odds ratios. Because the odds ratio before was very clean. There was no arguing. The parent dropped out, didn't drop out. There's no scaling issues of what's a 1 unit increase. Do you mean a 1 unit increase in years of education? Hours of education, a 1 minute increase of education? E to the b, the logistic regression odds ratio, is still going to, how big that odds ratio is still going to depend on the scaling of what x is. So we're going to see some other funky things about it in a second. So it's not quite the same. But the key is that it varies based on the scaling. So you need to ask yourself, when someone says the odds ratio is 2 for something, that just in logistic regression, that means a 1 unit increase doubles the odds. Now what is a 1 unit increase? And they need to tell you what that 1 unit is. Is it a year? Is it a week of intervention? Is it an hour of studying a night? What does that 1 unit mean? Now, there's kind of interpreting this. It's kind of some straightforward if we assume that, again, thinking that that one on the dependent variable is some negative outcome. You dropped out, you were arrested, you died, whatever. If the regression coefficient is equal to 0, if b is equal to 0, what's the odds ratio going to be? The odds ratio would be e raised to the power of 0. E raised to the power of 0, anything raised to the power of 0, is always equal to 1, which is just kind of a wild thing, but that's for another course. Well, I mean, if you kind of do it mathematically and you approach it, but it's still, anyway, I always kind of get a kick out of something raised to the power of 0. It's 1, but it is. But think about it this way. That's telling you your odds ratio is 1. What's the increased odds of dropping out if e to the b is 1? Well, a unit increase, my odds are now 1 times greater. Well, that's the same thing. Nothing. Whatever my odds were, I multiply it by 1. It's now 1 times that. It's the exact same. I should have switched some stuff around. On the other hand, if b is greater than 0, so your regression actually, I want to take a step back. This is kind of handy too because, think before a regression coefficient equal to 0 in multiple regression. What did that tell us? If your regression coefficient was 0, that meant no effect. Right? That means it's a flat line. Whatever happens to x, nothing's changing on y. Even with the odds ratio, e to the b, if b is 0, it's the same thing. Nothing's happening. Your odds ratio is 1. There's no difference. Whatever your x is, it's exactly the same all the way across. If b is greater than 0, so now you've got a positive, that indicates, well, e to the b then, e raised to the power of b, whatever, will be greater than 0. I'm sorry, greater than 1, which just indicates increased risk. So if e to the b is, say, 2, that means a unit increase in risk now doubles the previous risk. I'm sorry, a unit increase in your predictor doubles the risk, doubles your odds. Notice also, notice it's not adding 2 to the odds. It's multiplying it by 2. So a unit increase doubles the odds, and another unit increase doubles the odds again. Oh, that's why in hindsight I should have switched some slides around, but we'll get to that. So if the regression coefficient is positive, it means it's going to increase the odds of the outcome. Usually, because if the outcome's a negative thing, it means it's a risk factor. It's having some effect increasing your risk of something bad happening to you, assuming that's the way we're going. If the regression coefficient's less than 0, then e to the b, I was just saying e to the b, the odds ratio, the logistic regression odds ratio is going to be negative, which means a unit increase is going to lower the odds. So say if e to the b is 0.5, so b is negative, the odds ratio won't be negative. It'll be less than 1. So if the regression coefficient's less than 0, if the regression coefficient's negative, the odds ratio, e to the b, will be less than 1. It'll still be between 0 and 1. But that just indicates decreased risk, in essence, so if assuming the outcome's a negative thing. So if e to the b is 0.5, then a unit increase in x cuts my risk, cuts the odds of the outcome in half. And another unit increase cuts it in half again. And another unit increase cuts it in half again. So it keeps kind of magnifying as we're going along. Now, one thing that's kind of cool with this is, as we saw earlier, note this sort of inverse symmetry. Not inverse. I know I just want... Well, actually, in this case, it is inverse. What am I saying? It is inverse in this case. An odds ratio of 4 means a unit increase in x increases my odds by 4 times what they were before. So if Philip and I are both here, and we're looking at how many hours we spend partying every week, and the odds ratio is 4, and I spend 1 hour extra partying, my odds of failing this course, the odds ratio is 4, are 4 times now what Philip's are, because he stayed behind. I've partied 1 extra hour. I'm now 4 times. On the other hand, if I start off here, and I'm 4 times the odds, and I party 1 hour less, my odds ratio is 0.25. I'm going down by 4. Up by 4, down by 1, down by 1/4 to get back where you are. So you could take an odds ratio, any odds ratio you can take your odds ratio of 4 and say, well, a unit increases my odds by 4. Or you could just flip it and say, well, a unit decrease in that risk factor lowers your odds by 1/4. And that's perfectly valid. This kind of gets at that risk strength sort of. You can flip the sign. I'm sorry, not flip the sign. Do the inverse. Maybe this is a better way to symbolize. Do the inverse of it. Unit increases by 4. Unit decreases by 1/4. Pretty cool. And notice as we were just I think you already started to see what's very different. And so our regression coefficients in logistic regression, we're already seeing they're a little different. In ways it's very similar. We get a regression equation. We're calculating regression coefficients. 0 means nothing's happening. A 1 means it's a positive. Less than 1. So there's some of the same patterns, but we're talking about odds ratios now. And you want to do e to the power of the regression coefficient instead of just interpreting the regression coefficient. Nobody does. No one really tries to generally interpret just the regression coefficient. We almost always will make them e to the b's and talk about them as odds ratios. Another key distinction I think we've already started to see is the effect is multiplicative instead of additive. In multiple regression, when I study 1 more hour a week, we saw my GPA increase by 0.2. I study another hour, my GPA gets another 0.2 added to it. I study another hour, my GPA gets another 0.2 added to it. In logistic regression, every unit increase is multiplying by the odds ratio. So if back to my partying example, though we'll only make it a 2 now. If every hour of partying a week doubles my odds of dropping out, of failing the course. I party 1 hour, my odds have doubled. I party 2 hours, I'm doubling that double. So it's 2 times 2, it's gone up by 4. I party another hour, it's 2 times Got 4, it's now 8. I party another hour, it's 16. Odds ratios can get really big. In that sense, the effects, I should say, the odds ratios may be small, but the effects can get very big very fast because it's multiplicative. And this is where the scaling comes into play. If your independent variable has a big range, 0 to 100, and people are at 10 and 50 and 30 and 80, a 1 unit increase may have a very, very small odds ratio because it's such a small sliver across that range. But if you take like a 1.1, let's say it's only a 1.1 is your odds ratio, so it's a little bit above 1, a little bit of risk. And you're going from 10 and maybe a lot of people around a score of 30 and then up to an 80. You go from 30 to 31, it goes up one, now it's 1.1 what it was. Another 1.1 is 1.1 times 1.1, now it's 1.21. Now it's 1.3 something. Now it's 1.4, 1.6, 1. It gets up. It can be a pretty big difference. Even small ones, if you're multiplying it 10, 15, 20 times. So you've got to kind of look at the scaling of your independent variable and not just look at, oh, this odds ratio is so small. But ask yourself, well, it's small based on what scaling? What are and so people will often rescale their variables in what seem like odd ways. Hours, how many hours you work a week. Well, that makes a lot of sense, but that could be a big range, 0 to 40. So instead, the units will be 10 hours. So it's going to be a 1 is 10 hours a week, a 2 is 20 hours a week, a 3 is 30 hours a week. So you're saying a 10-hour increase in working leads to what effect? Instead of a single hour, just to kind of avoid having to do a 1 hour times 1 hour times 1 hour times 1 over and over again. So again, the key is this is a big deal if you're trying to interpret the effect, particularly when it's a continuous predictor. Ask kind of, to get a sense of how big the effect is, look at the odds ratio, but then look at different values of your predictor. Okay, what's the increased risk if the mom had 10 years of schooling versus 16 years of schooling? And do odds ratio, so it'd be 11, 12, 13, 14, 15, 16, and take that odds ratio and multiply it by itself 6 times. And that would give you the increased odds from 10 to 16. You have to play with it a little bit to be able to interpret it clearly.